Okay, so this is going to be lecture 2 of kinetics. I'm actually going to do lecture 3 when you guys come back to school, okay? Because I don't think I want to fit everything in along with your lab videos, okay? So, so far, the rate laws that we have examined um, show the relationship between the rate of the reaction and the concentration of the reactant, right? However, we also want to know the relationship between the concentration of the reactant and time. Like, how does concentration and time affect each other? Okay. Or how does the concentration or the time affect the concentration, more like? Okay. So, if you think about a reaction, this used to be pretty um, common in the 90s to talk about like and the early 2000s to talk about like chlorofluorocarbons in the atmosphere. Okay. CFCs, or chlorofluorocarbons in the atmosphere, they threaten our ozone layer because they produce compounds that basically make holes in the ozone layer. Okay. And one of the reasons that these CFCs actually threaten the ozone layer is because of the uh, time that it takes to consume them, like the reactions that will consume them, it takes so long that, and it's so slow that even if we stopped adding CFCs to the atmosphere, now the concentration in the atmosphere would only decrease very slowly or by very little because of the time that it takes to break them down. So this is where integrated rate laws come in. You can calculate based on the concentrations how long it's going to take to break down those reactants into products. Okay, like 20 years, 50 years, who knows? Okay, so this is where integrated rate laws are helpful for predictions like that. Okay, so let's talk about the zero order integrated rate law. So we are going off of the regular rate law that we have done based on a reaction concentration and the rate of the reaction. Okay, so on the right side, you have your calculus work. If you're interested, you can look at it, but I'm only going to talk about the algebra. And I said that for the integrated rate law, because you use integration to arrive at the equation or to derive the equation, you can't, you have to kind of accept the integrated rate law as it is presented and just know how to use it to predict rate. Okay, so here is the zero order integrated rate law. So we're going back to our very basic we're going back to a very basic reaction with reactant A decomposing into products. So we know that the rate law for a zero order reaction is this: rate equals the rate constant times the concentration of A raised to the power of 0. When you raise A to 0, that's nothing, right? So rate is actually equal to the rate constant. So that is the rate law for zero order. Rate is equal to the rate constant. Okay. Now, this particular integrated rate law, algebraically, it also makes sense. So just follow along with me, okay? We know that rate is represented by the change in the concentration of A over the change in time, right? And we have a negative sign in front of the change because of the fact that it's a reactant and it's going to get consumed. So reactants are being lowered, right? So if you say that rate is the change in concentration of A over the change in time, that is going to actually be equal to your rate constant, right? Then, then you can um, isolate the change in the concentration of A by rearranging these variables so that the change in the concentration of A is equal to negative K times delta T. Okay? Now let's talk about what actually delta concentration of A is. Okay? It's the difference between the concentration of A at time T at any given point in the reaction. Let's say you start the reaction at time 0 and you're like 5 minutes into the reaction, then concentration of A at time T would be at 5 minutes. What's the concentration of A? Okay. And the concentration of A at time 0 is just going to be the initial concentration. So this is just initial concentration. Okay. So the delta concentration of A is actually the change, what it is right now, concentration of A at time t minus the initial concentration, that is equal to negative K. And then the change in the time is the difference between what it is now and what it was before. So it will be like 5 minutes, and t at time zero is just zero, right? So then you have kind of an equation to calculate the concentration of A at time t. If you just rearrange this equation by adding the concentration of A at time zero, the initial concentration, to the right side of the equation, then you get this equation that kind of represents a line. Okay? So you can calculate the concentration of A at time t, that's equal to negative K times the time plus the initial concentration. Okay? So this actually represents a linear or a line, a linear graph, y equals mx plus b right here. Okay? So if you wanted to plot this on the y-axis, you would just have, whoops, on the y-axis, you would have the concentration of A at time t. On the x-axis, you just have time. Okay, could be minutes, could be seconds, could be hours, days, whatever. CFCs would be years. Okay, so you have the concentration of A at time t in your y-axis, time in your x-axis, and your slope is negative, and the rate constant is the value for the slope. Now, this is really important. The rate constant itself is not negative, okay? It's just the slope that's negative, but the value for the slope is your rate constant, okay? So K is your rate constant, that's your slope, and your y-intercept is going to be the initial concentration of A. So if you have a bunch of data, okay, let's say you have time and concentrations. Let's say you have concentrations of some compound, um, A. You can plot it, okay, like 0, 10 seconds, 20 seconds, 30 seconds, etc. And you have the concentrations to go with those, like X, Y, Z, whatever. And it gives you a straight line when you plot concentration on the y-axis and time on the x-axis. If this data results in a straight line, you can say that you have a zero order reaction. Now, if this data does not result in a straight line, you do not have a zero order reaction, okay? If you have a zero order, it will be a straight line. If it's not a zero order, then the line does not fit. It is not zero order, okay? So it has to be a linear relationship to be zero order. Now let's look at integrated rate law for first order reactions. Now I want to just make sure you got to memorize this, because this is the equation that's not given on your equation sheet. Zero order is not given, okay? Next, let's talk about first order integrated rate law. So for the first order rate law, where we were just looking at concentration and rate, that's your rate law. Rate equals rate constant times the concentration of A raised to the power of 1. Okay? Now, here is the work to finally get to this. This is your integrated rate law for your first order reactions. Okay? This is something that is actually in your equation sheet. However, the work for it is based on integration. So we are not going to be going over that, but if you're interested in the calculus, you can look at it. You don't have to memorize this, but just know that this is the one for first order. First order uses natural log, okay? So let's look at it. So you have the rate law just when you were looking at rate and the concentration of reaction, concentration of the reactant. And the integrated rate law is looking at time um, and concentration. Okay, so here again you have a straight line, or you have a linear relationship. The natural log of the concentration of A at time t is equal to negative kt plus the natural log of A at time 0, which is your initial concentration. So here it is in a graph form, okay? Here is what it would look like if you were just plotting concentration of A versus time, okay? The concentration of A is decreasing as time goes forward, as the reaction goes forward. So concentration goes down. All right. Then if you wanted to see if it was first order integrated rate law, what you do is you take your data. So here's your data. But you need another column now. So this will be time. This will be concentration. And you would have to do ln of the concentration of A. So time would be like 0, 10, 20. I'm just going by seconds. Concentration is like X, Y, Z. And then you would have to be like ln of the X, ln of the Y, ln of the Z, etc. If those values, if you plot this column and this column together, and then you get your straight line, that means you have a first order reaction, okay? Because this data would actually, if you plot time and just concentration, you wouldn't get a straight line. So it's definitely not zero order. You would get a curve like this, okay? If you get a straight line for time and concentration, that's zero order. If you get a straight line for time and natural log, that's first order, okay? So your x-axis is the natural log of the concentration of A at time t. And then the x-axis is your y is natural log of concentration of A at time t. X-axis is time. The intercept is the y-intercept is the natural log of concentration of A at time 0. So you can actually calculate the concentration at time 0 or initial concentration from here. You just use the reverse of the natural log. And then your slope is again negative, and you have a rate constant that is k. Again, the rate constant cannot be negative. It's just the slope that's negative. The value for the rate constant is always going to be a positive number. Okay? Okay, so that is first order. This one is given to you. You don't need to memorize this one. All right, let's talk about second order. Now, the first difference you would see here is that second order integrated rate law seems to produce a line with a positive slope. So that's important, okay? The calc work is in the second slide. Obviously, we're not going to look at it, but if you're interested, you can. But here is the rate law for second order, okay? And here is the integrated rate law for second order. So this one is just reaction, concentration versus rate. This is time versus conc. Okay, so in your y equals mx plus b here, y is your 1 over the concentration of A, and then time is again your x-axis. So for all three graphs, time is always your x-axis. The y-intercept is going to be 1 over the concentration of A at time 0. Y is 1 over the concentration of A at time t. The slope is positive here, and the rate constant is k. Okay? Just forget this is just a stoichiometric coefficient particular to that picture or the example I got it from. You don't have to worry about that. Okay? So the slope is k. This is the only one that has a positive slope. So if you plot the data, so let's add another column to your table now. Okay? This one would be 1 over the concentration of A. So you would just be like 1 over x, 1 over z, 1 over y, etc. Oh, this is y, this is z. Okay? If this and time gives you a straight line, then you have a second order integrated rate law. Okay? I feel like I should do this better somewhere. Hold on. All right, so we have a blank slide. Let's do it like neater. Okay? So let's say I have time, I have concentration, 1 over the concentration. Oh, sorry, ln of concentration, 1 over the concentration. So what you would be given is usually in a question time and concentration. This is what your lab gives you too, these two columns. Okay? So time can be anything, right? Here I'm going to say seconds, 20, 30. So what you would do is as the reaction is proceeding, okay, let's say you have A going into products. As the reaction is proceeding, you would try to calculate the concentration of A, or you try to measure it using some kind of technique. What is the concentration of A at time 0? You already know that. That would be your initial concentration, okay? And then you would measure 10 seconds later, what is the concentration? Let's say it's X. 10 more seconds later, at the 20-second mark, what is the concentration? At the 30-second mark, what is the concentration, etc. Okay? Then you would make one graph. You would try to see what order this fits into. So once you have your concentration, you can do a simple calculation for each value. What is the natural log of the concentration of A? That'll give you some value here, some value here, some value here, some value here. And then you could also do 1 over the concentration of A. You just take the concentration and you put 1 over it. And then you calculate what's this, this, this. Okay, so now you have your data points. Now you'll need 3 graphs to figure out. So here's your second graph, and here's your third graph. Whoops. For integrated rate law. Okay, here's your third graph. If I could draw it, I could show it. Okay, there we go. Now, if you plot these two sets of data, time and just the concentration of A at time t, time in seconds, and this is just A at time t, and you get a straight line like that. Whoops, that should be straight. You get a straight line like that. That indicates that you have a 0 order reaction. Okay? The other two graphs will not be straight. They'll be curvy. Okay? That means you already know what your initial concentration is. And especially if the initial concentration was unknown, this is a way to calculate it. Okay? And your slope is going to be negative k. All right? Then, again, slope itself, the number is the rate constant. That is a positive number, just the slope shape is negative, okay? So let's say you want to do natural log of A and you have 4 values. That would mean you would do this and this. You would plot time in the x-axis and in seconds, whoops. And then your y-axis would be just natural log of A at time t. And if you get a straight line for that, this won't be a straight line and this won't be a straight line, okay? If you get a straight line for that, that means you have your first order integrated rate law. The order of the reaction is first order, okay? And again, your slope is your rate constant, just a positive value, but you have a negative slope for the actual equation. Then, if you wanted to do If you wanted to check to see if it was second order, you would do this column and this column. And here you would have 1 over the concentration of A at time t, and this would be time. And you end up with a line that is straight, okay? You would end up with a line that is straight with a positive slope. That positive slope is going to be k. Your y-intercept is going to be 1 over the concentration of A at time 0. So you can calculate what your initial concentration was, and that will be a second order reaction. So if your data gives you a straight line for this will be first order. If it's this one, it's 0 order, like that. And if you get this one, it's second order. And what you will be provided for the question is just these two columns. You will have to figure out whether it's first or second or 0 order. Okay, so 0 order is just concentration on the y-axis. First order is natural log of the concentration on the y-axis. And second order is 1 over the concentration on the y-axis. Okay, the x-axis stays the same, it's just time. And the slope changes and the rate constant changes. Okay, now that was integrated rate law. Let's talk about half-lives. So I know that you haven't done nuclear chem, which is where you would have learned about half-lives, but no issues. Half-life reactions are pretty easy, okay? They're based on the integrated rate law. So half-life of a reaction, also denoted as T1 half, is the time required for the concentration of the reactant to fall to 1/2 of its initial value. So the reason this is constantly used for nuclear chem is radioactive material break down spontaneously, right? So when that happens, you can check to see what the half-life of that material is and determine how stable it is. Something like francium, I think, has a half-life of minutes, which means if you have a lump of francium, you'll only have half of it in like some amount of minutes, less than an hour, okay? So you can pretty much apply this to any reactant. If a reaction is happening, the half-life of that reaction, the reactant in that reaction, is going to be the time in which it goes down to half of its original concentration or initial value. Okay? The half-life of a reactant actually depends on two things: the rate constant, K, and how much you started out with, obviously. And it's different for different reaction orders. So let's look at the first order reaction half-life. This is the most common one that you find in questions. So this is your rate law for the first order. This is just written a little differently. If I go back, you'll see. So you can either write it like this, or you can rearrange it, and you can move your concentration of A at time 0 to the left of the equation, and you can get this, this version of the equation, okay? So it's just easier to derive from there. So this is the integrated rate law. Now let's talk about what the concentration of A at time t really means when it's in terms of half-life. So at a time equal to the half-life, when t is equal to T1 half, the concentration is exactly half of the initial concentration. So concentration of A at time t, when t equals the half-life, is going to be 1/2 of what you started out with. So you can rewrite concentration of A at time t as 1/2 of the concentration of A at time 0, or 1/2 of the initial concentration. So that. Then we take that and we replace this with that. So that's what's happened here. Okay? Then the concentration of A and the concentration of A cancel out, leaving you with this expression, which is ln of 1/2 or ln of 1/2 is equal to negative kt, and t is just T1 half now because it's half-life, okay? Now, if you use your calculator and you do ln of 0.5, you are going to get this number, 0.693. And then you can resolve this expression to isolate T1 half, where T1 half is going to just be negative 0.693 over negative k, okay? So it's going to be just negative 0.693 over negative k is equal to t1 half. The negatives will cancel each other out, giving you this expression, t1 half is equal to 0.693 over k. Now I think, yeah, first order half-life reaction is actually given in your equation sheet, okay? You don't have to memorize this. Now, this is basically saying that your first order reaction half-life is independent of the initial concentration. So let's look at this graph and then I'll tell you how to interpret a set of data that's given about half-life, okay? So for first order reactions, the half-life is independent of the initial concentration. That means you are lowering the concentration of A from 0.2 to 0.1, that is 1/2 of what you started out with. That time, okay, that it took, whoops, wrong place to draw brackets. That time that it took to go from 0.2 to 0.1, that's your half-life, okay? How much time did it take to lower the initial concentration by 1/2 of its original amount? So that's your half-life. Here, I think it's like 7 seconds, right? But look at the second half-life. When you go from 0.1 to 0.05, that's your second half-life. You go from 0.1 to half of that. This is still seconds, 7 seconds. So the half-life for first order is independent of the initial concentration. The half-life does not change. The half-life is constant for first order reactions, okay? So if you get a table with data with the concentration decreasing, but the half-life is not changing, you got a first order reaction. You can write the rate law for that now. You can write the integrated rate law for that now. Once you determine the reaction order, you have many things that you can do and calculate the rate constant, okay? This is unique to first order reactions. Now remember, T1 half is equal to 0.693 over the rate constant. If you know your half-life, like let's say you have a table with half-life in it, like 7 seconds, okay, and you know 0.693 is the natural log of 1/2, you can easily calculate what your rate constant is. It's just going to be 0.693 over 7 seconds, okay? And that'll give you the rate constant with units of seconds to the negative 1. Very easy. You can use the half-life equation to calculate the rate constant for the reaction, okay? Now, you don't even need concentration for it because it is independent of concentration. See? Okay. Now, let's do second order reaction half-life. So here's the integrated rate law for the second order reaction. Okay. Again, at a time equal to the half-life where T is equal to T1 half, the concentration is exactly half of the initial concentration. The concentration of A at time T can be replaced by 1/2 concentration of A at time 0, which is, which is going to just be initial concentration. So I plug this in, I plug this term in there, okay, and I get this equation. 1 over 1/2 concentration of A at time 0, blah, blah, blah. And then T is just T1 half, okay? So I'm trying to isolate T1 half. So I rearrange my equation. And now I have this expression on the right. So 1 over 1/2 of concentration of A at time 0, if you divide something by another fraction, then you have to rewrite it, right? 1 over, you have to like flip it. Yeah, so sorry, blank for a little bit. So you have to flip it, okay? So instead of dividing 1 by 1/2, you are actually multiplying 1 by 2 over 1 concentration of A at time 0, okay? You're taking the fraction and flipping it because that's what you do when you divide something by a fraction. Okay. How much time do I have? Okay. So if the bell rings, just, it's fine. I'm in school, okay? So you have you have this now, 1 over 1 half concentration of A, you flip it, then you end up with this. If you do that, 1 times 2 over 1 um, times concentration of A, you end up with this. That's where that came from. So 2 over the concentration of A minus 1 over the concentration of A, the denominator is the same. That's going to just give you 2 minus 1 over the concentration of A at time 0 times K. Because if you divide this side by K, you're going to get K on this. So this is the second order half-life. Okay, second order reaction half-life equation. T1 half is equal to 1 over the rate constant times the concentration of A at time 0, or initial concentration. So let's look at what happens in a second order half-life. The half-life definitely depends on the initial concentration, and the half-life is actually inversely related to the initial concentration. Okay, that means look at what's happening. You're going from point 2 to point 1 here. The first half-life is like a few seconds, maybe 2.5 seconds, right? But when you go from point 1 to 0.05, the second half-life gets longer. It's inversely related. As the concentration drops, the half-life increases. Concentration drops, half-life increases. Okay? So the third half-life is even longer as you go from 0.05 to like 0.025. Okay? So you have the half-life increasing with the decreasing concentration. So if you have the initial concentration, you can solve for the half-life here. Or if you have the half-life, you can solve for the initial concentration. Or if you have the half-life and the initial concentration, you can solve for rate constant. Okay? Then let's look at the zero order half-life reaction. This is the zero order integrated rate law. This one is not given to you. Remember, you have to memorize that. We replace A at time t with 1/2 of A at time 0, because at T1 half, you have half of the initial concentration. Then you're just, bye kids, have a nice break. You're welcome. Bye bye. So you have 1/2 of the concentration, initial concentration equals the negative K T1 half plus the initial concentration from the integrated rate law. You are trying to isolate T1 half here. So if you take this term, bye bye, you're welcome. If you take this term here and you subtract it from this side, okay, you'll get this expression, because this is one whole initial concentration, this term, and this is 1/2 of that. So 1 minus 1/2 is going to leave you with 1/2, okay, which is what this is, 1/2 of the concentration of A at time 0. And then if you divide by K, you're going to have K in the denominator here. Okay? So this is 1 whole minus 1/2. Okay. So this is the expression for half-life for zero order. T1 half is equal to the concentration of A at time 0 over 2 times the rate constant. So let's see how that affects your half-life. Half-life is dependent on the initial concentration. They are directly related. Okay. As the concentration decreases, the half-life is also decreasing. So they're directly related. They both fall down. So you're going from point 2 to point 1. Your first half-life, I don't know how many squares this is, 1, 2, 3, 4, 5, 6. This is in 20, 20, 40, 60, so whatever. Okay, so here's your first half-life. Okay, it's long. And then second half-life is half of that. Okay, and then the third half-life is half of that. So as the concentration falls down, the half-life gets shorter and shorter and shorter. Okay, so if you have the initial concentration and the rate constant, you can solve for T1 half. Or if you have the half-life, which most often you will have, like if they give you a graph, okay, the half-lives won't be marked out. They'll just give you concentration and time, just like that, okay? And then they'll just show you how the concentration is decreasing. Your job is to say, oh, hey, look, this is what I'm starting out with. And look, this is like where it's 1/2 of the initial concentration. So this must be my half-life then. You can actually get your half-life from the graph, okay? So if you have your half-life from a graph and you have your initial concentration, you can calculate your rate constant using the zero order half-life reaction equation, okay? So that was integrated rate law and half-life. That is it for kinetics lecture 2. When you come back, we will continue on from here. All right. Hope you guys are having a nice break and having some relaxing times. Okay. Bye bye, everybody.